Hey everybody, welcome to this session. Really excited to be here and talk about distributed training using PyTorch with Kubeflow on AWS and Amazon SageMaker. My name is Amit Kalawat. I'm a Principal Solutions Architect at AWS, and I work with our enterprise customers as they transition to cloud and transform their businesses. I've been with AWS for almost 4 years now. And joining me today is my colleague, Kamaljit Kurmi. I'm going to pass it over to him for his introduction as well as the agenda for the workshop.
Thanks, Amit. Hey, everyone. Welcome to this workshop. I'm Kamaljit Kurmi, working as Senior AI/ML Specialist Solutions Architect. I'm with Amazon Web Services for almost 3.5 years now, and I specialize in containerized and machine learning applications. Now, let's take a quick look at the workshop agenda. Now in this workshop, we are going to use Amazon EKS Cluster 1.22 version and AWS Kubeflow Distribution 1.6 to run a PyTorch-based distributed data parallel model training example. And while we run that example, we will also create a machine learning workflow using Kubeflow pipelines, and we'll use Amazon SageMaker to provision a fully managed infrastructure for model training. And if these services are new to you, don't worry, we're going to cover those services in detail during this workshop. Now, as a part of AWS Kubeflow Distribution 1.6, we have done a lot of improvements. And one of them is that we are now providing a one-click automated solution to really automate the end-to-end installation and deployment of Amazon EKS Cluster and AWS Kubeflow. And we're going to demonstrate that using the Terraform scripts as part of this workshop. And because this installation takes around 30 minutes, we'll get you started with that as the first thing. That's step 0. And while the installation scripts will be running in the background, we'll come back to the slides. We will discuss the basics of distributed training and why we should consider that. We will also talk about the landscape of tools and services that AWS has to offer to support distributed training architectures. We will then deep dive into AWS Kubeflow 1.6 feature set and what differentiates that from the open source Kubeflow. And then towards the end, we have 2 end-to-end code-based hands-on labs to provide you a hands-on experience on how Kubeflow pipeline works and how you can use Amazon SageMaker for distributed model training. So as you see, we have a lot of content to cover. And without taking any more time, I'll probably pass it back to Amit to walk us through step 0. That is basically giving you access to the AWS accounts and getting you started with the installation script. So with that, Amit, over to you.
All right. Thanks, Kamaljit. All right, so let's talk about step 0, which is about provisioning the AWS account and logging into AWS Cloud9 to run our scripts, which will be provisioning the infrastructure as well as the Kubeflow dashboard. So if you see this screen, right, there are 3 blocks which we are showing just to walk you through the high-level flow of the installation steps. So we will be using Eventbox, which is going to help you provision AWS accounts, and from there we will follow guided steps, and I will show you those guided steps shortly. And using those guided steps, we will be provisioning a Cloud9 IDE environment, and on that we will be downloading some scripts, and then we will run them in the background. And while they are running, we will go through we will keep going through the other parts of the workshop. So let's quickly go ahead and actually walk you through the instructions as well as provisioning of the AWS accounts. So right now, there are 2 important links which you want to be aware for this workshop. They are being shown on the screen right now. We will also share these links with you on the chat so that you can actually also access them from your chat window and then open them in the browser. These 2 links, the first link is for accessing the AWS accounts for the labs in the workshop. The second link is specifically around the instructions and talks about the architecture which we'll be building as part of this workshop. So we will open both of these links in a new browser window. And let me open up my first link. All right. And let me also open the second link.
By the way, I'll request our moderators to paste these links in the chat so that it becomes easier for our audiences to from there.
All right. Okay. So now the second link. Let's talk about the second link, which has the instructions at a very high level before we go to the first link. The second link talks about the architecture which will be stood up, but at a very high level, the workshop is divided into 3 sections. you're talking about logging into AWS account, you're talking about setting up of your Amazon EKS and Kubeflow on AWS, and then we will be running use cases as part of the third section. You can follow me as I'm going to go through these first two sections to create the AWS accounts and infrastructure. But again, these links are available to you on GitHub. Please feel free to follow them and walk them through at your own self-paced fashion. If you want to do it at your own pace and time and schedule, these both of these links will give detailed instructions of logging into AWS account, and then also creating your running the scripts which will be required for standing up the EKS cluster as well as Kubeflow dashboard. So having said that, let's go back to our first link and hit launch, and let's provision our AWS account. So it is giving me a capture. I'm going to select bridges. All right. So on the next screen, we are able to see that a temporary AWS account has been shared with us. We'll click here to access, and it's going to bring us to this next page. You don't need to do anything. Simply accept terms and login. And on the next page, you will see sign in with email one-time password, and there are other ways. Everybody can use their personal email address to get a one-time password, which will be used to actually access the AWS account. So I'm giving my email address over here. Okay, so hopefully we will get the passcode in a short span of time. So I'm going to go check my email, and then we can actually log in. So it looks like I got my password. So I'm going to enter it. And you can also do the same thing for your account. All right, so that means sign-in has been successful. So the next screen will have this page, and you can click on AWS console on this part.
One other thing is, I think we can probably take a pause here just to make sure that everybody has received their the single link passcode. And also, Amit, can you maybe maximize your browser window? Probably.
Sure. Let me do that, and I'm going to make it a little bit big.
Yep.
That helps. Hopefully that is better.
Oh, yeah, that's much better. Thanks, Amit.
Okay. Thank you. So, yeah, I think we'll just take a quick look at the chat window just to make sure that if people have any questions, we can help answer them. So while going through that, and if for people who have been, like if you are on this page, if you click on Open Console, that's going to bring up the AWS page or Management Console. So all right, great. So I am logged into my AWS account, and now I can go ahead and actually get started with running the rest of the steps. And for folks who think if they're running behind, please feel free to chime in and ask your question, and we'll be there to help you. So a few things which we have to note as part of this particular page is we need to make sure that we are running in Oregon, which we can check from this part of the page. We are running in US West 2, which is the Oregon AWS region. The other thing is, which I mentioned, is we have to make sure that we are using Google Chrome for best experience for running Kubeflow dashboard as well as accessing AWS console. So having said that, let's quickly go ahead and open up Cloud9. So you can do that from this top place on the console by typing Cloud9 and then clicking this icon. And AWS Cloud9, for people who are not aware, is a web-based IDE for writing debugging code. For people who are in software development, you're used to writing code in IDEs, which might be on your laptops or workstations. This is a web-based IDE which can be accessed over browsers. So we will create a new environment, and for that, I'm going to click over here, and let's give our Cloud9 environment a sample name. So I'm writing Kubeflow workshop. You can leave the description as blank. For next step, we will choose, we'll keep the first option of environment type as default. For instance type, we will choose M5 large. And the third part for platform, we will choose Ubuntu 18.04 version. And please make sure that you choose Ubuntu because this is important for the instructions in this workshop. And for cost saving settings, you can choose 4 hours. You can keep rest of the settings as same, and then click on next step. You will be brought to this page where we can review all the settings, and we can keep everything as is and click on create environment. Okay, so while this page is actually coming online, it's going to take probably 30 seconds to 1 minute. While this is coming up, let's quickly go back to the other page where we had the instructions, and let's quickly walk through the architecture, which will be set up as part of this particular workshop. So if you see this image over here, I'm going to try to make it a little bit bigger so that you can see it better. So essentially, we completed step 1, which is logging into a browser. Step 2 is creating of a Cloud9 environment. We're doing it right now. As soon as that is completed, we will be downloading certain scripts from GitHub, and we will be running those scripts. And those scripts, when they're running in a background, they will be creating EKS cluster. They will also create an EKS worker node as well as Kubeflow. And we'll talk a little bit more about that momentarily. So let's go back and see. So it looks like our Cloud9 environment is made available. And just looking at the chat, if people are at this step, if you have any issues, please feel free to actually send your questions on the chat. So we need to do 2 things when we have logged into Cloud9. The first one is we need to click on this link on the right hand side. You see my mouse pointer, and over there we'll scroll down, we'll click on AWS settings, and over here we will actually go ahead and select on this particular option where we are disabling the managed credentials. And we are doing this because we want to assign right kind of permissions to our Cloud9 environment so that it can go ahead and create all the necessary resources. We're talking about EKS clusters, VPCs, subnets, and other AWS resources which will be required for this workshop. And let's see how we will assign our Cloud9 environment that additional permission. So for that, we will go ahead on, again, top right-hand side of the browser. We'll click on this button T, and then we'll hit Manage EC2 Instance. That's the second option. So, and this screen is going to bring up the AWS EC2 instance, which is actually running behind the scenes. So Cloud9 as a managed service runs on EC2. So this EC2 is actually helping run our Cloud9 environment, which I just put up. So we will select that EC2 instance from here, if you see, from this part, and then we'll click on Actions. We'll click on Security, and we'll click on Modify IAM role. So this particular option. And when we are on this page, we'll have this drop down where we can actually assign the IAM role, but we don't have an IAM role which is created right now, which has good permission. So let's create a new IAM role by clicking on the link. I'll go back over here. It's this link. I selected this. It brought up a new tab. And on this page, we will create a new IAM role. And for people who are not aware of what AWS IAM service is, it's Identity and Access Management. It's a service which can help you control access to each and every resource within AWS. So I selected Create Role, and then by default, the first option is AWS Service. We'll keep it as is. We'll scroll down, and we'll select EC2 over here. So I selected EC2, and then I'll go on the right-hand side, and I'll select Next. On next page, we will add permissions to our role. So I'll quickly go ahead and type administrator over here so that we can filter the roles which have administrator, the policies which have administrator privileges. You see this policy. And based on your use case, you can choose the right kind of role. We'll click Next. And over here, we'll give a name to our role. So I'll type Kubeflow workshop. So I gave this role, and then I've scrolled down. We'll keep everything as is, and we'll go ahead and click on Create Role. So if you see, the role is getting created, and looks like our role just got created. We have this green banner up top. So our role is created. We need to assign this role to our Cloud9 environment. We'll go to the previous tab, which is right next to it over here, where we had that drop-down menu. I'll hit refresh on this page just to make sure that the roles are refreshed, and then we can select this role right over here. As soon as this role is selected, we'll click on Update IAM role. All right. So that completes the prerequisites to actually kickstart the installation. So we have our environment running on this page. The other tab, let me make it a little bit big so that people are able to see it properly. I'll close this. I'll close this as well as this window. You can go ahead on this screen, select this plus sign. If you see over here, plus sign and create a new terminal. So on this new terminal, now we are ready to clone our Git repo. So the first thing is what I'll do is I will go ahead and make sure that we have the right credentials allocated. We assign the role, just want to make sure that we are able to access that role programmatically. And we are able to do that. So Kubeflow workshop shows over here. Now quickly go ahead and we'll copy the Git repo. And the command to clone the Git repo, I have this already on this particular tab. I'm going to copy it, but you can also, I'll also show you, it is also there on the instruction set. We'll show that momentarily. Like as soon as I click on this, it's going to clone the Git repo. Going to the instructions, just want to make sure that you are able to see the, let me close this tab. Yes, if you go to the step to install, which is one of the steps in the workshop, and we will share this particular link directly on the chat window also for people who don't have it. If you scroll down on this page, the link to clone the Git repo is right over here. If you see over here, Git clone. So I'm running this step right now. In fact, I just ran it. So we'll go ahead and move forward with the next step. Okay, so I'm on this page. I'll quickly go ahead and I'll cd into the folder which we cloned. And if I list all the files, you can look at the files from here also. So we have two installation scripts. One is install kubeflow.sh. The second is a kubeflow dashboard.sh or shell script. So we will be running the first script, the install script to kickstart the installation. So you can do that by doing a // install eks kubeflow.sh and then hit enter. So this script is going to run for 30 minutes. It is going to create AWS resources like VPC, EKS control plane, EKS worker nodes, and will also deploy Kubeflow on it. And it is using Terraform behind the scenes. And I can show you some of the scripts which are running on the Terraform. If you go to this particular folder on left-hand side, Kubeflow manifests. And while I'm doing that, you can continue to, you can keep this tab running. It will run in the background for next 30 minutes or so. So if you come back to Kubeflow manifest, you can go to deployments. You can go to vanilla. So there are a lot of ways you can set up Kubeflow deployment on AWS. We are choosing the vanilla option. There are other options as well. And you have Terraform scripts for each and every option. So if I go to vanilla Terraform, if you see main.tf, for people who are familiar with Terraform, I think it's an infrastructure automation tool. I'll talk a little bit about that momentarily in a slide which is coming up shortly. But for people who want to dive deep into this Terraform script, they can look at all the modules which have been created over here. Like for example, over here we are actually talking about. If you see this part, it is talking about the number of nodes which will be running on this cluster. There are a lot of variables where we are defining the size of our EC2 instance, which will be stood up as part of the worker nodes, and so on and so forth. So if you're interested, please do take a look at these files. All right, while this is running, let's go back to our presentation and then keep moving forward. All right, let me go to a presenter view. So we talked about these two links. Next up is the at a high level Kubeflow on AWS deployment options. And as I was talking a few minutes ago, we are using Terraform in this particular workshop as an automation option for deploying of our Kubeflow infrastructure. And Terraform is essentially an open source infrastructure as a code software tool. It actually codifies cloud APIs into declarative configuration files. I showed you two config files which had .tf extension. Besides that, there are other ways to deploy Kubeflow as well, like automated way of deploying Kubeflow. And one of the famous ones is Kustomize for people or for teams who or developers who are very fond of Kubernetes, they may have heard about Kustomize as a way of doing Kubernetes native configuration management. Kubernetes introduces a template-free way of application customization that simplifies the use of off-the-shelf applications. So you can actually do a lot of config management using Kustomize. And there are instructions available to deploy Kubeflow using Kustomize as well. We'll share those. We'll share those as part of the workshop as well as on your chat window. The third option which we see over here is Helm charts. Again, Helm is a package manager for Kubernetes. The Helm charts help you define, install, and upgrade even the most complex Kubernetes applications. The Terraform scripts which we are showing over here, they are also using Helm charts behind the scenes. And of course, you can take a look at that if you want to dive deep in that folder structure. So I have talked a little bit about the way we are setting up our implementation or installation of Kubeflow as well as EKS and other resources. Let's quickly switch gears and talk about why distributed training is important, and how we are going to do that as part of this workshop. And so for that, I'm going to pass it back to Kamal.
Thanks, Amit. So let's start with some high-level understanding on why distributed training and why would you consider that. Now today, if you see data scientists and researchers who are building up deep neural networks using open source frameworks like PyTorch, MXNet, TensorFlow, they have found out that they get much better accuracy if they train their models with significantly large amount of data set. Now, this especially in the use cases like computer vision and natural language processing. However, the challenge with that is that when your data set grows, it takes a long time to train your model. Now, the longer it takes for you to get to the training results, that means the slower will be your time to market. Now, if you want to really speed up your training, you actually have to consider a few options. One of them is you can go back and optimize your code. However, you can only so much you can do with your code, and at some point you probably would like to provision more compute resources. Now, when it comes to provisioning more compute resources for distributed training, there are two different paradigms. One is scaling up your machines, and the second option is to scale out. Now, with scaling up, I mean, you can replace your existing machines with more powerful machines, which have a more number of GPUs. And this is always a preferable option because when you have multiple GPUs in one machine contributing towards your model training, these resources have to communicate with each other while the training is happening because the gradient synchronization needs to happen. And then having them all in one machine is much faster because there are no network overheads, which you otherwise have to consider when you are using multiple machines. However, there is only so much of resources that you can add to one single machine. And when you hit a wall with that and you need even more performance, that's when you have to scale out and include more number of machines in your cluster. This means you are actually taking your data and your code and really training them on multiple machines together. Now, the rule of thumb here is that always consider scaling up, and only when you need more resources and more performance, then consider scaling out. Now, for the purposes of this workshop, it's a distributed training workshop, we will be considering a scaling out option. We will be using multi-node cluster where every node will have a GPU, and we'll demonstrate how you can run distributed training across those machines, in the GPUs that are provisioned in that. Now, with that in mind, let's quickly take a look on how distributed training works and why it speeds up. Now, we will be considering here the use case of deep learning or training, right? And the first step that you have to do is split up your data set into batches. And then you have to pass on these batches sequentially to your deep neural network. And each one of these batch will go through a forward pass. Then the losses will be computed. We'll do a backward pass. We'll compute the gradients, and then we'll update the model parameters, right? Which will be the parameters for your neural network. Now, the bottleneck here is that these batches are being processed in sequence. That means most of the resources of your machine might be underutilized because they are able to only process one batch at a time. And the second option is to really use multiple machines in your cluster. And in this scenario, you will copy your model to each of these machines, and then you will spread out your batch to these machines so that these machines can work on those batches in parallel. So effectively, that means we are able to train on a bigger batch size at the same time which results in speeding up your training as compared to the first option where you were able to process these batches in sequence. Now let's look at the tools and services which AWS has to offer to really support this kind of distributed training architecture. So fundamentally, we have compute instances. These are Amazon Elastic Compute Cloud instances, which you can bring together, build up your own cluster, and can use that for distributed training if you have the required expertise. But over the years, we have built services like Amazon Elastic Container Services and Amazon Elastic Kubernetes Service, which greatly abstracts away the cluster management complexity so that you can focus on your applications. Now, these are the container orchestration services, which requires your application to be containerized. And to manage those containers, you can actually use our service, AWS Elastic Container Registry Service, where you can push your images, you can version them, and then you can pull those images when it is required and schedule them on the cluster or the platform of your choice. Now, this all works great, right? But when you enter into the machine learning domain, you definitely need more capabilities which are above and beyond just these infrastructure capabilities. That's where our Amazon SageMaker service comes in. Amazon SageMaker is a fully managed service which helps you create, train, optimize, and deploy your models. You can use this service to really spin up a distributed training cluster. You can run large-scale hyperparameter optimization jobs. And the good thing here is that the infrastructure is managed for you. Even when it comes to deployment, you can write a few lines of code and you can deploy a model without worrying about provisioning the infrastructure, provisioning the load balancer, scaling your infrastructure up and down when the demand grows and shrinks. And all of these capabilities comes inbuilt in SageMaker. Now, the whole idea here is that while we try to scale up our machine learning environments, we want to provide you with a managed experience that comes with Amazon SageMaker. And the whole purpose or the focus of this session would be on how we can use the Amazon SageMaker capabilities right from within the Kubernetes environment. So while you continue to standardize on Kubernetes for various different organizational reasons, maybe you might have existing investments, or you might want to keep Kubernetes as a central control plane for all of your workloads, you can still leverage all the innovations and capabilities that comes available with Amazon SageMaker. Now, we did talk about containerizing your workloads, and containers could be something which is counterintuitive, could be counterintuitive to some of the data scientists who have not worked on this before. Now, we'll take a minute here to really explain what containers are. Now, by definition, containers are the standard unit of software that allows you to package your applications, the related dependencies, configurations into a lightweight portable package, which can consistently run from one platform to another. Now, just imagine you are working on a machine learning use case where you might be working on any of the open source frameworks like TensorFlow, PyTorch, MXNet. Now, all of these frameworks come with different versions, and they have a lot of other interdependencies with other libraries and tools. And you could also have libraries at the CPU and GPU level. And you see, right, there's so much to manage and then ensuring that all of these libraries works well together. But once you have sorted that out, you can actually package all of these things together into one package, which is a container, and can easily distribute that across a distributed training cluster. And you can be rest assured that you can reproduce the results which you have seen in your local development environment. Now, AWS also makes available its own deep learning containers, which have the optimized version of the open source deep learning frameworks like PyTorch, TensorFlow, and the others that we see on the screen. You can build, test these containers. You can even extend these containers, add in your own libraries and make it your own, and then can schedule it on the platform or cluster of your choice. Now, the frameworks and libraries that are included in these AWS deep learning containers, they are tested and optimized to run on AWS cloud. And they are optimized for I/O, they're optimized for storage, they're optimized for EC2 instances that are available for you for model prototyping and training. So I think a deep learning container definitely is one of the things that you should definitely consider. if you want to speed up your training, not only the training, but also the development cycle of it, because when you spin up your development environments or IDE environments by these container images, you already get access to the frameworks and libraries so that you can get started with your code right away. And even when you have to deploy your models, you can leverage these containers to provide you with the training environments, which needs access to the libraries and framework which are included as part of this. Now, let's briefly see how machine learning works on Kubernetes. Now, as a data scientist, you have to instruct Kubernetes on the desired state of your machine learning workload. So that could be, a data scientist might say that I need 2 GPUs for model training, and I need probably 10 CPUs for model deployment. And you can actually define these specifications in a file, which is normally written in YAML format. And you submit this specification to Kubernetes control plane. Now, Kubernetes control plane reads the specification, which also includes the container image, which will have your training script and all the dependencies which the training script needs. EKS will retrieve that container image from the ECR repository and will schedule that on the cluster of worker nodes that it is managing, right? And it will do its best to ensure that the desired capacity is met as you have specified in that YAML specification file. Now this works well. However, there are still some challenges when we are trying to run a machine learning workload on Kubernetes environment. And those are like, it could be a little counterintuitive to data scientists to work on these YAML files and worry about formatting and other stuff, and who are used to really working on the Python language. Plus, Kubernetes environment natively does not provide machine learning capabilities like experiment tracking, workflow management, distributed model training, model deployments. And if you want to build those up, you'll have to build those up from ground up on the Kubernetes environment. And when you do so, you will realize that your operational overheads might increase in managing those worker nodes when you're trying to ensure that they're optimally they're optimally utilized to serve those capabilities to your data scientists. Well, the open source community did notice that, and they created a project called Kubeflow, which is basically a machine learning toolkit that runs on top of Kubernetes. Now, you can use a Kubeflow project to build and deploy machine learning systems at scale. And there are multiple different projects that come along with Kubeflow. Some of them are like Jupyter Notebook, which are basically a web-based IDE environments for model building, training, and interactive data analysis. You can use Kubeflow pipelines to build your machine learning workloads. And you can also use these projects for model training and model deployment. And there are many other projects apart from one we are showing in this slide. Now let's look at the architecture on how Kubeflow looks like when it is deployed on Kubernetes. Now Kubeflow is deployed on Kubernetes as any other application, right? So here in this diagram, you see that we have the Kubernetes cluster here, which has its own control plane. So if you are using Amazon EKS cluster, this control plane is managed by AWS. And then in this black dotted line, we are having our EKS worker nodes, which could be one or many. And on this worker nodes, we are deploying Kubeflow, and Kubeflow comes with its own control plane and data plane, right? And then the way Kubeflow is installed, there could be a couple of challenges that I want to highlight here. The first is the Kubeflow control plane heavy lifting infrastructure components like databases, authentication modules, storages. They are deployed on the Kubernetes worker nodes. So that means if you are trying to build enterprise-ready, highly available Kubernetes control plane component with a persistent state, it could be a little it could get challenging or a little difficult, especially in the cases where a worker node might fail or might crash, right? And the second thing is this control plane will continuously generate artifacts like the artifacts data related to databases, the min IO storages, or even the pod logs, which grows over time. So it means we need advanced monitoring capabilities to meet that growing storage needs. And the control plane is basically sharing the same resources with the Kubeflow worker nodes. So that means right-sizing your cluster as well as storage volumes could again get challenging and might result in increased operational overheads. Now, the good part is you can combine the open source Kubeflow with the innovations that AWS has to offer through the AWS specific distribution, which we call as Kubeflow on AWS. Now, Kubeflow on AWS is a product which you can use to build highly scalable, reliable, and secure enterprise-ready machine learning platforms through the integration of AWS managed services. Now, let's look at how those integration with AWS managed services actually looks like. So we'll go back to the previous diagram. This is a snapshot of all the integrations which Kubeflow 1.6 offers. Just to walk you through a few of them, we provide integration with Amazon Cognito for user authorization and authentication. We have integration with Amazon S3, which could be used to save a pipeline artifact storage, and Amazon RDS to save the pipeline metadata. We also have integration with AWS Deep Learning Containers, the one we just talked about in the previous slide. You can actually use those optimized frameworks that comes with Deep Learning Containers with your training cluster, with your model deployments, as well as with your Jupyter notebooks, right? So if you spin up your notebook with the Deep Learning Container hosting your notebook server, you get the access to all those optimized frameworks and the most common open source libraries right away. Plus, a few other things to mention here is that you can also use Amazon EFS and FSx for Lustre file system with your Jupyter notebooks and with your training clusters as well. Now, this is one of the ways where you can really meet the needs of training where you need high performance, you need millions of IOPS and hundreds of gigabytes of throughput. Those needs could be met with these file systems. And also you can use these file systems for collaboration and reusability of the data set, which has already been transformed, right? So you copy the data set in these file systems once, and then you can either share it with the other members of your team, or you can share it between different training clusters if they are depending upon the same data set. A few other things to mention here. We also have integration with Amazon SageMaker. We used to have SageMaker ACK operators, which are basically AWS controllers for Kubernetes. This used to be one of the ways where you were able to submit SageMaker jobs from the Kubernetes control plane. And now these ACK operators are also available in the Kubeflow 1.6 distribution. So that means you can now submit jobs to Amazon SageMaker right from Kubeflow notebooks, as well as from Kubeflow pipelines using SageMaker components. And we're going to cover SageMaker components for Kubeflow pipeline in our labs as well. Last thing to mention here, observability, monitoring are some of the key requirements from many of our customers. So we provide integrations with Amazon Prometheus and Amazon Grafana to track Kubeflow system metrics. And we also have integration with Amazon CloudWatch to track your container logs. So even if your cluster crashes, your worker node dies, or your pod fails for any reason, you will always have those logs available to you. And you can go back in time, look at the results of your previous training runs, or debug through any issues that you might have seen. Right, so I'll take a quick pause here. I know we have covered a lot of content in these slides. So feel free to type in your questions in the chat, and our moderators will do their best to answer them. And yeah, I think probably take a pause here. And while our moderators are helping answer your questions, I'll probably be handing it over to Amit to really walk us through the next slides, which are basically introduction to Kubeflow pipelines. So Amit, please take it away from here.
All right, let's talk about Kubeflow pipelines. And for people who are not aware, right? And so Kubeflow pipeline is part of the Kubeflow project. It is a platform for building and deploying portable, scalable machine learning workflows, which are based on Docker containers. And there are a few important aspects of Kubeflow pipelines. Like you can say that there is one user interface for managing and tracking experiments and runs and jobs. Then you also have an engine which can help you schedule multi-step ML workflows. And Kubeflow pipelines also provides you an SDK or a software development kit, which can actually help you programmatically access the Kubeflow pipeline engine from your Jupyter notebooks as well. And why are these three or four things which I mentioned are important? Like essentially, these help in actually getting to the goals of Kubeflow pipeline. And what are those goals? Like, first of all, end-to-end orchestration, right? We're talking about enabling and simplifying the orchestration of the machine learning, the workflows. You're talking from training to data pre-processing to actually model deployment, as well as inferencing. You can stitch together workflows which can help you perform all of these things in an automated fashion. The second important aspect is ease of experimentation. Kubeflow pipelines can help you run and manage numerous ideas and techniques as you're trying to train a model, and you're trying to go for different trials and experiments, and trying to go for different model combinations, and getting to which can help you find the answer to a problem in a faster fashion. The last important aspect is ease of reusability or reusability. So Kubeflow pipelines actually help you enable your team members and other people in your teams, because they can reuse components which you have written, and they can reuse, I would say, like reuse part of your work and create end-to-end solutions without rebuilding each and every time. So those are some of the key aspects of Kubeflow pipelines. Let's talk about Kubeflow pipeline components in a little bit more detail. So what is a pipeline component, right? So essentially, when we talk about Kubeflow pipeline, it is actually constructed out of pipeline components or pipeline steps. And what does that mean? That essentially means that these individual steps, which can be implemented as a Docker container, and they contain the actual code for doing one of the functions around a machine learning workflow, right? If you're building a model, or you're training a model, and then actually you're evaluating a model, and then you are actually deploying that model for inferencing. Those three steps can be actually constructed as three separate pipeline steps, and you can actually have your containers for each one of them run as part of Kubeflow pipeline. So you are basically lining up your steps in a chronological order, or in the order the way you want your machine learning workflow to run as, and then that will define the steps of your pipeline. And as we see in this diagram, because since we are running Docker containers for performing these various functions of a machine learning workflow, we have to make sure that our Kubeflow pipeline infrastructure is connected to a registry or a container registry, which can actually help you manage or act as a container repo for managing your container images. So I've talked about Kubeflow pipelines as well as Kubeflow pipeline components. Let's see how you can actually construct a sample pipeline by looking at a sample code. So on this image, on the left-hand side, if you see, we are showing a sample pipeline. And on the right-hand side, we are talking about basic, I would say, building blocks. And when you're writing a code for building a pipeline, you are actually, first of all, defining your pipeline components. Those components can be for a specific use case or a specific function in your machine learning workflow, for training, for data transformation, or for prediction. You will actually line up those components in the order in the order which they have to be executed, and then from there you will actually construct the pipeline definition, which we see over here, the pipeline function which is being built, and then you will actually create an official pipeline object by actually using a pipeline decorator, which we see over here. So by creating an official pipeline decorator or a pipeline object, you can actually then compile the pipeline and then submit that to the Kubeflow for running it. So we talked about Kubeflow pipelines. We talked about pipeline steps. Let's see how Kubeflow pipeline and Amazon SageMaker components for Kubeflow, they actually work together. So as I was explaining that essentially you are implementing various steps in a machine learning workflow as Docker containers, and those containers they are run as Kubeflow components. So a lot of partners and a lot of open source solution providers, they have built their components which can actually be run from within your Kubeflow pipelines for running these different job functions, or I would say machine learning different functions within the machine learning workflow. From Amazon SageMaker team as well, I think we have built the SageMaker components for Kubeflow pipelines, and we're talking about multiple components which can range from model training, hyperparameter tuning, as we see on the screen, pre-processing, model deployment. and these can be called from within your Kubeflow pipelines, and we'll see that as part of our examples. And of course we'll see when we are running that example. But before I move ahead, Kamaljeet, if you want to add anything on top of whatever I just mentioned on this page.
Yeah, I think it's a great description of SageMaker components. It's just that SageMaker components again comply with the component specification which Kubeflow open source community has defined, and these components basically requires you to pass a certain set of parameters that we're going to see in the upcoming lab, and it abstracts away all the complexities on how it actually makes a call to the SageMaker service. So once you have passed the parameters defining how you want to run your model training or how you want to deploy your model deployments, these components will take care of all the rest of interacting with the actual SageMaker service.
All right, thank you. So let's go ahead and take a look at our script. I think because we ran it like some time ago, so I'm gonna go and check on the script. So I have my browser window over here. So I think looks like the script completed. So it actually created an EKS cluster. It created a VPC or a virtual private cloud within my AWS account, and it also it also set up the Kubeflow on it. So for us, as part of the next steps, because we have to access our Kubeflow environment from the Kubeflow dashboard, let's quickly bring up the Kubeflow dashboard. And for that, we have one more script, which is Kubeflow dashboard. So I'm going to do a // and I'll write Kubeflow dashboard .sh. So as we're running this script will add the right permissions in the kube config file so that we can actually access our Kubernetes cluster from this shell. It is also doing a port forwarding for us to access the Istio ingress gateway, which is essentially our mode of entry into the environment and access Kubeflow dashboard. And why we are doing this? Since we are setting up a vanilla Kubeflow implementation, which can be accessed by default passwords, we are not exposing this implementation on public internet. We are doing port forwarding. So within our Cloud9 environment, we can access our Kubeflow dashboard. And for that, since we see that the port forwarding is also happening right now, we can quickly go ahead and select preview on top, and then select preview running application. All right, so let's quickly access our Kubeflow dashboard. And for that, what we'll do is we'll hit preview, and then we'll click on preview running application. You see it's on top of your screen over here. As soon as I click this, it is going to open up the Kubeflow dashboard on this part of the browser. You can always open this whole tab in a brand new window by clicking this link, and it will bring up this page. And we can access this page by giving user ID password, which is a default user ID password for Kubeflow. And you can access that user ID password in the instructions. Let me quickly bring up that page over here. So if you scroll this page on the installation steps, the default user ID password is mentioned over here. It is user@example.com, and the password is this. So let's quickly put this on our browser and hit login. So we have entered the Kubeflow dashboard, and then going to make it a little bit bigger. So we are accessing Kubeflow running from within Cloud9 environment using port forwarding, and now we are ready to actually go ahead with our next set of workshops and start running the Jupyter notebooks. And for that, I'll pass it back to Kamalji.
Okay, now thanks Amit for having us log into the Kubeflow dashboard, and this is how it looks like. So the first thing I would like you to verify is that on this top dropdown, you see this particular namespace, kubeflow-user-example.com. We have kind of standardized this for every single account that is being provisioned as part of our event engine platform. And once you have this dashboard appear for you, we'll go to the left navigation and click on the notebooks link. Now, this is a place where we'll see the list of all the notebook servers that you might have provisioned in the past. So we'll go ahead and click on new notebook to provision a new notebook server. Okay, So you can give any name of your choice. So I'm going to go ahead and give a name AWS Workshop. Okay, so namespace will be the one you see here in the dropdown. And then you have to select Docker image. Now, Docker image is the container that's going to host the notebook server that will be used by Jupyter Lab. Now, here, this is a place where you can leverage one of the AWS Deep Learning containers that we provide you out of the box. You can choose between PyTorch and TensorFlow. So we're going to go ahead and choose Jupyter PyTorch 1.12. Now, again, the kind of IDE environment that you choose to use is dependent upon the this particular container image, and you can build up this container image from ground up, and you can mention the URL of that image using this custom image option. Okay, so you can either mention the URL of Docker Hub repository or the ECR repository. For this lab, we're going to use PyTorch 1.12 version of Docker image. In CPU, we'll just use one CPU and 5 gigabytes of memory. I'll request everybody to use one CPU because that's all we need to run this particular lab. We have limited resources provisioned for each of the cluster, so let's stay a little bit frugal in using these resources. We don't need GPUs for our Jupyter notebook. We'll be using GPUs for our training cluster that will be spun up in SageMaker service. Workspace volume will leave this to default, and data volumes we will just skip it. Just to mention here, in case you decide to use Amazon EFS or Amazon FSx for Lustre file system, you can use any of those file systems either as your workspace volume or data volume. Finally, in the configuration, we're going to select this particular configuration, which will allow your SDKs from your notebook to access Kubeflow pipeline service. And we'll click launch here. Now this will start the provisioning process for our notebook server. Again, as we mentioned before, Kubeflow notebooks support 3 notebooks natively. That is Jupyter Lab, RStudio, and Visual Studio Code. Again, you can build up your own container image and can use any other IDE of your choice as part of this Kubeflow notebooks. So it looks like my notebook has been provisioned. So I will click on the connect button here. So it's taking a minute to spin up my Jupyter Lab interface. There you go. So we are logged into our Jupyter Lab interface. For those who have worked on this interface before, they might be familiar. In the middle, we have the ways to spin up our Python 3 kernel, log into a terminal, and other options. And on the left side, we have the way to browse through our code, and any notebook that will spin up will be shown at the left navigation. And then there are other links here where you can look at the terminals that you're using. And if you decide to clone your Git repository, you will see it here. Now, the first step, we'll go to the Git options here, and we will clone our repository. Now the README documents that Amit has walked us through, those are your friends, right? In case you are left behind for any reason, every single step that we are following in this lab is mentioned in those documents. So you will be able to go through the step-by-step instruction in the documents and can still execute these workshops. So this Git URL is mentioned in the use case README as well, and we're gonna ask our moderators to really type this in the chat as well. So I'll click on clone, and this will clone our public GitHub repository. I'll double click on this URL, in this folder, and then we'll click on the workshop, and finally to PyTorch distributed training folder. This is where all of our notebook examples are kept. So we will start with step 1.0, which will create a pipeline, and that pipeline will run distributed training on SageMaker, and it will also deploy the model on the SageMaker environment. So before we walk through what this notebook is actually doing, I will request everybody to click on this first cell and execute it. Now there are multiple ways you can execute the cell. Either you can enter Shift Enter, or you can select this cell and click on this play button on top. Okay, so this will execute a cell, and then what we're doing here is we are installing the latest SageMaker libraries. And while this cell is running, you will see this particular tags here. You will have star within this. And once the execution finishes, we will see this converted to a number. Okay. The only thing that we have to do after we execute this cell is that we'll have to restart the kernel. The reason being, when we install SageMaker libraries, they get installed on the instance of Python that have brought up the notebook environment. For our existing kernel to get access to these libraries, we'll just have to go ahead and restart it. And the way you will do it, you will go to this kernel menu option, and you will click here on Restart Kernel. Okay, so it's a restart, and it's going to take a couple of seconds to restart it. And then we'll go ahead and click on the second cell, and then we're going to run all the cells underneath it in just one command, which you can use from the Run menu option, and then select Run selected cell and all below. Okay. Now the reason we are running all the cells together is because the pipeline that will be created as part of this notebook, it takes around 10 to 15 minutes. So while we talk through the details on what this notebook is doing, we can get that pipeline started. Cool. So while the notebook is executing, let's see what this notebook is doing. And even before we talk through how the pipelines are getting created, let's probably take a few minutes to understand how SageMaker service work. Now, for anybody who has worked on SageMaker before, this could be a refresher. And for people who are new to SageMaker, this probably will give them a context on how SageMaker service actually works. Now, as a data scientist, if you can directly interact with Amazon SageMaker, you can call SageMaker APIs. And when you do so, the SageMaker APIs are received by SageMaker control plane, right? And in this APIs, you will define a couple of things. You can define the deep learning container image that are provided to you by SageMaker. Again, this is one of the options that you can choose. And this is something that can help you get started faster, because those container images will come pre-installed with the open source frameworks and many of the open source libraries. However, you can also bring in your custom container as well. Okay. And while we are going to pick up the containers from SageMaker, we will still be injecting our own training script. So this is called the script mode in SageMaker, where we are leveraging the SageMaker containers to give us access to the PyTorch, TensorFlow, and other libraries. But then still we are providing our own training script, because that is something we have built for our own organization and has our own secret recipe. Okay, so the training script and the container is part of the API, and we will also define the cluster configuration which we want SageMaker to spin up to run our model training. Okay, so for example, here I have said of SageMaker, I want to spin up a cluster which should include 2 worker nodes, and that worker node could be of any specific type. It could be P3 instance, it could be a P4 instance, which have V100, A100 GPU instances. So anything that you require should be part of your API. SageMaker will bring up those worker nodes in a cluster. Now this cluster is an ephemeral cluster. This will run only for the time that your training is running. Okay. So once SageMaker spins up this cluster, it will pick up the deep learning container image that you have specified in your API from the ECR. It will initialize its environment, and then it will pull in the data set required for your model training from either of these 3 data sources. Okay, so it could be Amazon S3, it could be Amazon EFS file system, or it could be FSX for Lustre file system. Okay, so the data set is pulled in, and it will start training your model. Okay, and once the model training is completed, the model artifacts will be pushed out to Amazon S3 service to the URL which you'll specify in the API as well. And all the logs and metrics will be available in CloudWatch as well, so that you can go back in time and can look at the performance metrics and can get access to the logs. The advantage here is that this is a fully managed experience. You don't have to do anything manually. SageMaker will handle bringing up this cluster, and it will terminate this cluster as soon as the training completes. So it's an ephemeral cluster. So that means you are only paying for the time that your training is actually running. And also you can use and take advantage of Amazon Spot instances, which are basically the unused EC2 capacity in the AWS cloud. Amazon Spot instances gives you up to 90% of discount as compared to on-demand instances. So that's some of the benefits that Amazon SageMaker provides on top of the managed experience that you get. Okay, so this is the architecture that will look like when we will submit the job to Amazon SageMaker. Now let's go back and see how we can create our workflow, and in that workflow, one of the steps, how we can use that step to submit the training to SageMaker to really execute in this fashion. Okay, now as first step, we are importing all the basic libraries. These libraries are like Kubeflow, SDK, Boto3, SageMaker, and other libraries like YAML and JSON, which will be required by our notebook. And then we are actually executing a notebook in US West 2 region. However, this notebook you can execute in any other region of your choice. Here at this point, we are kind of pointing to the SageMaker training and inference deep learning container images. And then we are getting a SageMaker role. This is a role that we'll be assigning to the SageMaker cluster, so that the cluster can get access to pull in the data set from S3 and also push out the artifacts back to S3, right? So it needs permissions to make those calls. Finally, we initiate a session on SageMaker, which will be required to initiate the SageMaker job. And then we will be downloading the Cypher10 dataset. Now, in this example, we will be covering the training script that we are using and kind of the convolution neural network that we have built up. And that's an image classification model. So we are kind of training a model on the Cypher10 dataset, and we'll be using the final model artifact to run the inferencing on our images. Okay, so we download the dataset, and then we have to upload the dataset back to S3, because as we have seen in the architecture, SageMaker requires our training dataset to be either in S3 EFS or FSX. So for that reason, I am choosing S3 for this particular lab, and we'll upload a dataset so that SageMaker cluster can pull in the data for model training. And finally, we are also loading the SageMaker components from the URL. Now, we have the SageMaker components version V2 recently launched, which are completely based on SageMaker ACK operator, which uses SageMaker Golang SDK in the background. This kind of is in par to the latest SageMaker APIs. And this is kind of the strategy for us to really enhance and add in on more feature to that ACK operator and make it available to you as SageMaker components. Now, we also had SageMaker component V1 version, which was based on Boto 3. So here in this example, we are using combination of SageMaker component V2 for training and the SageMaker component V1 version for model creation and deployment, so that we can demonstrate that you still have the flexibility to choose any version of your choice and can run your training deployments accordingly. Okay. Finally, the custom training script that we are using in the SageMaker cluster, that has to be uploaded to S3 as well, so that SageMaker cluster can pull that training script from S3 and can use that for model training. And then we have a few of the helper functions to define where our data is stored in S3. We have some functions to really pull in the artifacts from the SageMaker training job. Cool. Now the good part here is we are creating a pipeline, using this annotation. So that means we are using a DSL annotation, just a domain-specific language that comes in with Kubeflow pipeline SDK. That means once you annotate this function with this annotation, Kubeflow will convert this function into an actual pipeline. And this function will have all the components defined in sequence, which will define the execution flow of your final pipeline. And the first component here is the SageMaker training component. And here you are passing the parameters defining how you want SageMaker to run your training. So you are passing in your deep learning image for training, which will define what kind of deep learning framework and libraries you want access to while the training happens. You also specify the kind of number of instances you need and the type of instances. These have been parameterized. So if I go up to the method header, you will see I'm using P3 2x large. P3 is a kind of compute instance, which is used for high performance compute requirements, and it provides you access to V100 tensor core GPUs. And I'm using 2 of them. That means I'll be splitting out my data set and will be processed by these 2 instances in parallel. And each of these instances will have 1 V100 tensor core GPU. Okay, and then we can pass in any hyperparameters that are required by our deep learning neural network and other configurations around networking where we want to run a cluster in. Okay, so with that, we will have a second step in a pipeline, which will retrieve the S3 model artifact URL from the first training run. And we will have the third component where we will create a model which will point to the S3 location where our model artifact is stored. We will also be using a custom inference script, which will basically kind of deserialize the input image that my client will be sending, so that deserialized image could be converted into a tensor and could be passed on to the final model. And the output that we receive, we will be serializing it back to the JSON output, which will be sent back to the client. Okay. And the last component here is that we will use that particular model artifact created and we'll deploy it on SageMaker. Okay. And then once you have defined this pipeline in the Python function, we will use Kubeflow pipeline SDK to compile that. This compiler will convert that Python function into Argo specific YAML file. So Argo is an underlying engine which will execute your pipeline. So your function needs to be converted into a YAML specification that Argo engine can understand. Okay, so this particular YAML file is created here. And then you will use the Kubeflow pipeline client SDK to submit this pipeline to the pipeline service. And then you will see these two links at the bottom of this cell. And you can click on the run details here, and you can see the pipeline actual execution. Okay, so it will take you to the runs, runs option in the left navigation, and you see here that the SageMaker training job is still running. Okay, if you click on this, you will see that this will give you all the input parameters that you have passed to your training run. Once this training completes, you will be able to see your output model artifacts as well, and you can click on this link here, logs, to see and get access to the SageMaker logs. And if you will see here, we are using SageMaker component v2, which uses the SageMaker ACK operators in the background. So the kind of parameters that you pass in this component, that SageMaker component converted those parameters into a YAML file, which is of type training job. And this YAML will be submitted by ACK operator to the SageMaker service. Okay, so we'll let this training to run, and we'll go back to our Jupyter notebook, and we will discuss the training script that we have used for this. Okay, so here we ran this particular notebook, so it's still running, and the training script is present in the folder called code, and this is the training script that we have used in our SageMaker training job. So let's run on what this training script is doing quickly. Now, one thing to note here is that we are using all the open source PyTorch libraries. We haven't written a single line of code which is specific to SageMaker that will make this training script kind of platform agnostic, and you'll be able to run the same training script both on the Kubernetes environment as well as on Amazon SageMaker. So that gives you extreme flexibility, right? You don't get tied into any kind of service, and you can just take in this script and can run it the way you want to in any other platform as well. And specifically, we are using the torch.distributed module, which has a support of PyTorch, and it supports the communication primitives for multi-process parallel multi-node training, which PyTorch provides. And this is a place where we are creating our image classification model, which is created using a combination of convolutional, max pool, and linear layers. And to those layers, we are applying a ReLU activation function during the forward pass of this neural network. Okay, and then we are downloading the Cypher10 dataset. So here, the download is marked as false because we have already uploaded this training dataset to S3, so we don't have to download it again. We are using distributed sampler module here, which will load the sample of data in a distributed fashion, which will be required for a distributed training. And finally, we are using data loader class, which will combine the data set and the distributed sampler together and will give us a single process or multi-process iterator over the data so that we can use that to distribute our training across different machines, which are part of our distributed training cluster. Okay, and then let's go through the training function. The first thing we're doing is this particular script can run on machines which have CPUs only. Or if your machines have GPU, it will leverage GPUs. The way it is doing it is checking if the CUDA support is available. And a CUDA is basically a kind of parallel computing environment. It provides you with the application programming interface so that your softwares can get access to the underlying GPUs. So if CUDA is available, the device variable will point to CUDA. Otherwise, it will point to the CPU instances. Okay, and all the machines which are participating in the distributed training, they need to be initialized so that they can work with the PyTorch distributed data parallel libraries. And to do that, we have to call this init process script function, which comes with the torch or distributed module. Okay, so once you call that, here you basically provide the backend communication. You can either use Glue, you can use Nickel. We are kind of passing in the rank of machines, which is basically the index of the host where this process is currently running, and the world size is basically number of processes which are part of your distributed training. And finally, we are copying our model to a particular device, whether it's a CPU instance or a GPU, and then we are wrapping our model with distributed data parallel class if the distributed training is supported. and then we'll execute our training. And we're using cross entropy loss for our model training and the stochastic gradient descent optimizer. And as we always do, we go through the forward pass for a neural network. We will compute the loss, and then we'll go through the backward pass where we compute the gradients. And in the optimizer.step function, we will upgrade our model parameters. And finally, we will test, after every batch is executed, we will test that with the sample data to see if the accuracy is getting better with different iterations. And down below, all the parameters that we have passed to SageMaker, they are passed as CLI arguments. We're gonna retrieve those parameters using argument parser, and we will pass that argument parser to the train function so that training has access to all the variables or hyperparameters that we have passed, and you can use them during the model training. Right? So this kind of covers our training script. Also, we have the inference script that we talked about, right? There's a custom inference script. And SageMaker, though we are using the SageMaker deep learning container inference image, we can still inject our own logic when the inference is actually happening. So here we are using the model underscore function. This comes kind of a specification defined by SageMaker. We have to comply with that specification. But in model underscore function, I'm actually loading my model state dictionary into this network and passing it back to the actual model. And then when the inference will be called, I'm actually deserializing my image, converting into a tensor, and passing it to my model for the actual inference, right? And finally, I get the output, which I convert into JSON, and I send the JSON output back to my client. So we're going to use this when our model deployment will complete. Cool. Let's see how our training is running. So if you see, our entire pipeline has executed successfully, and we have done the training. If you see now, the training artifacts are generated as well. We will see the model artifacts are sent to an S3 location, and you have other parameters as well, like job status, access to logs. And finally, when you do the deployments, you will again have the access to what kind of endpoint has been created, because this is an endpoint that you will use to call from your client. And just a quick thing, when you are on your AWS console, you can again search your Amazon SageMaker service from this search text box, and you will come to this search SageMaker dashboard. Whatever trainings you have run, you can actually go to the left navigation, and you can look at those training runs from here as well. You will see that this is a particular training that we have run, and it was started like 10 minutes ago. And the model has been deployed, and the endpoint could be seen in this left navigation called endpoints. Okay, now I will go ahead and will copy this endpoint for my next step. Okay, I'll go back one folder up and will execute step 1.1 now, which is basically calling the endpoint that we have just created. So the only thing that you have to do is in second cell, you change this endpoint name to the one that that has just been generated, right? And then we will load this particular image. So I'm using a sample image of a dog, and I'm gonna send this image to the model for to classify that image, whether it's a dog or something else. I don't expect this model to give me the right result. It could give me a wrong result as well, because this is just a hello world example, which we have kind of trained on 10 epochs. But we'll see what kind of result it gives us. See, it gives us a bird. So I'm not surprised with that. But the whole idea here is that the distributed training is actually working. And once everything is sorted out, we have to go back to our code, optimize it, and maybe run it for more iterations, or maybe try it with different hyperparameters, right? And the last thing I will show here before we go to the next example, that when you go to the SageMaker training and you click on the logs, here on the top, or maybe right after this YAML, you see a link here, right? CloudWatch logs. So you can click on this link, and you can see the logs which are generated by our training script. Now this will take us to the CloudWatch logs page, where you will see a different log group created for every single instance type that has been provisioned as part of our training cluster. And the first image, which is considered as a master, will be named as Algo1, and the second the worker node will be named as Algo2, like here. Okay, so let's click on the first one, Algo1, and you will see here that all the epochs that our model has gone through, you will see the model training results here. And we are actually using the training data set, which has 50,000 images. Because we are using distributed data parallel, half of the data is being sent to the algorithm one worker node, and the second half will be sent to the second worker node. That's why we are only processing 25,000 images in this particular worker, and you can trace back and see that while the different epochs are running, we will see the loss kind of decreasing, and the accuracy will be improving. Okay, so I'll go all the way back. Okay, so maybe a little bit more. I'll load a little bit more logs. Okay. Okay, so this is where we are actually kind of processing 50,000 images, and only 25,000, which is 50% of this image is being processed there. And we started with a loss of 2.3, and if you see all the way, if you go down, the loss is kind of decreasing, and the accuracy is 0.26, almost there. And once we reach towards the end, the loss keeps on decreasing, and the accuracy kind of improve a little bit, right? So again, you have to optimize your code, and then can get better numbers on this one. So yeah, I think that concludes the lab 1. For lab 2, maybe Amit, do you want to walk us through the lab 2 example?
Sure. All right, so I think hopefully everybody can still see my screen. So let me make it a little bit bigger. So we just saw lab 1, which was about creating a SageMaker Kubeflow pipeline using SageMaker components and using SageMaker for doing training as well as inferencing. We have another example, which is using, again, it's a basic example of a Kubeflow pipeline, but essentially it is showing you that you can actually create recursive pipelines, or you can actually you can create logic which can run based on certain conditions. That, hey, if a certain condition is not met, for example, if your training loss is actually going beyond a certain level, you can continue training. So for that, we'll go to this particular example, which I have opened on my screen. You'll go to kernel, and you'll do restart kernel and run all cells. And again, this is a very basic example. It uses a regression model, and it is using the XGBoost open source framework for Chicago taxi dataset, where we are essentially looking at calculating the tips and actually finding out that, hey, if our target label, which is tips, and if you're not able to find out if the loss is going beyond a certain level, it will keep on retraining the model. So at a very high level, if you want to start from the top, we install the Kubeflow pipelines and we import those libraries. We actually have these components which we are loading for functions like training, for prediction, even transformation. So we have those running over here. And if you scroll down, then we will define two functions. The first one is over here. We'll actually define a train until low error, where we'll train a model, we'll do some predictions, we'll calculate the regression matrix, and based on if the regression metric, which is again we're looking at mean squared error, if it is going beyond a certain value, we'll actually retrain. We'll train some more, and then we are calling this function in this part of the notebook, where we are defining a pipeline, where we are actually loading the training data, we are preparing the data, and then from there we do the first model. We train our first model, and then from there we actually run that function, which we defined over here. So at the bottom, we have compiled the pipeline, and then we are running it. And just like the previous example, we can look at the run by clicking on this button, where it's going to open the Kubeflow dashboard, and it is going to show me this particular run as it is going through this its iterations. If you see right now, so it is still doing training, and after that we'll see it will actually collect the metric, which will define whether the training job has to run again or not. So and again, this particular example is not using SageMaker behind the scenes. Everything is happening within the Kubeflow as well as the Kubernetes infrastructure, which we have stood up. So let me see. So this one is still running. So what I'll do is I'll go back to my slide, and we'll wait for this this to run, and then we'll come back here shortly. So we're talking about this example. If I keep going ahead, so some of the key takeaways which we want to look at from this particular like overall workshop, I would say. So we talked about Kubeflow, and we talked about how Kubeflow provides end-to-end ML capabilities on Kubernetes. We also talked about Kubeflow and AWS distribution, which makes it easy to deploy Kubeflow. You can use AWS high-level services, which can actually enhance your Kubeflow and make it more reliable, um, and potentially help you run production-level workloads. We also saw that how you can actually use PyTorch with the open source deep learning framework to run distributed training using Kubeflow and also using SageMaker. And yeah, I think hopefully you liked what you saw. There are a lot of references which are available. We'll of course share these references on the chat as well. Please do follow us on the, like, there is a blog for Kubeflow and AWS. There is also a lot of instructions which talk about the Kubeflow manifest, as well as other links which are available. Before I move ahead, let me quickly go back and see our training job, how it is doing. Looks like, okay, it moved ahead. So I wanted to show one thing, that when we do prediction, we actually calculate the regression metrics. You see over here, the regression metrics are beyond a certain level, then it's going to trigger the training job again. And then it's going to continue doing that. It will do 2 or 3 times before it will actually come to a halt. So the example will keep on running. So it looks like it actually did that again. It actually again calculated in the second run. This is the mean squared error, which we see over here, and it is doing the training third time. And we can see that the pipeline is actually continuing to move forward. So hopefully this example will finish shortly. But then meanwhile, let me go back to the slide. We talked about a few references. Also, we want to thank some of the folks who have given like numerous contributions in helping us creating the content as well as the workshop. It will be great if you can actually give us some feedback of whatever you liked. If you didn't like anything, please let us know about that also, so that we can hopefully improve ourselves and make this workshop better going forward. If you liked anything, please let us know as well. And of course, you can reach out to us on LinkedIn. And of course, even if you want to look at the GitHub repo, you can clone it, and if you can create any issues if you come across any issues as such. So
so thanks everyone for joining us. We hope that you got a good introduction to Kubeflow and how you can build the architectures using Kubernetes and Amazon SageMaker. Again, as Amit said, please feel free to reach out to us on LinkedIn, on Amazon email forums, and please share your feedback through the survey so that we can continuously deliver these workshops and can come up with even more exciting content. So with that, thanks again.
Thank you.